Okay, let's begin. So today's another one of those days where I'm just going to be talking at you for a while. I just want to throw some ideas out there about summations, which we call series. We ended last class talking, so we're still in appendix. And we're talking more about series. Last time we saw that we could add the first n positive integers via this formula. So that has a nice little story behind it. And so we can move on. So this is one of the formulas that we want you to know. And there are a few more that is going to be very convenient for us to know, although I'm not really going to derive them for you. The second formula is, for our purposes, we'd want to know how to add the first n squares. The first I squares. So we're adding up 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to n squared. That also has a formula. This one is slightly more complicated. N times n plus 1 times 2n plus 1 all over 6. That's how you add up the first n squares. It will add up to an expression like that. We'll also want to know how to add up the first n cubes. So if we're taking a sum 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed all the way up to n cubed, it turns out that will be given by, curiously enough, the square of this expression. That's how you'd add the first I cubes. The last formula that you'd want to know, which is, probably should have been what we started with. It's more elementary than Formula 1, but this one had a nice story to it. That's why we started with this story, with Baby Gauss. This one just talks about adding up a constant. Right? So if you have the summation of a constant, what does that mean? Well, it just means for each I position, I equals 1, 2, 3, 4, the function output is just this constant number. So you're just adding that constant over and over. You're adding this constant to itself n times. The result must be n times c, or c times n, how would you do it, right? Because what you're doing here, this one is kind of easy to see. You're just adding c plus dot 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 plus c n times. So these are some nice formulas. To go into what we want to talk about, we also want to talk about some properties of series. By properties, we want to mean how do they work under arithmetic? If I'm thinking of the series themselves as objects, can I do arithmetic with these objects? Turns out we can to some extent. One property is the fact that, similar to limits and derivatives, if I have a constant times some expression that I'm adding the summation of, I can, in fact, factor that constant outside the series. What determines what's a constant? Well, the I represents your variable. Remember last time we spoke about how you can think of a sequence as a function where the input are the positive integers I, and the output is ai for each I. So here I'm just having a constant times a function. I can factor that constant outside. Now that one is also okay to understand, because this basically says this is CA1 plus CA2 plus CA3 all the way down to CAN. Clearly C is a common term that we can factor out, A1 all the way down to AN, and so this is just C times the summation of the AIs. So that should be clear. We can factor constants outside of series. They have this property. How would we add two series together? Well, there's also a property that tells us that series will distribute across sums. So if I have something like AI plus or minus BI, this is actually I can distribute the series across these functions. I can add up all the A's and then add up all the B's separately. So the series of a sum is the sum of the series, as it turns out. And that one is also not too difficult to see. If I'm adding up a bunch of things that look like this, for example, so that means I'm adding A1 plus B1, then I'm adding A2 plus B2, then I keep adding, all the way up to AN plus BN. Clearly, since addition is commutative, I can choose that I'm going to add all the A's first, and then add all the B's last. Because I can keep rearranging the sum. Now, this rearranging of the sum, I'll talk about it later. Because today we're going to talk about finding infinite sums. It turns out that this rearrangement thing has consequences for infinite sums. Or for finite numbers, a finite list of numbers, I can do this. And so that's just the sum of the A's plus the sum of the B's. So we can distribute series across sums. We can factor constants outside of series. I'm going to cover some of the basic properties here. So in Calc 2, you'll go over series in a lot more detail. But for now, we are going to use them in this class when we're computing areas. So I just want you to know how to deal with them algebraically. Let's actually do an example. Suppose I want to compute this guy. I want to add 100 terms that look like this. Now, of course, what does that mean? It means I'm going to take 2 times 1 cubed minus 1 squared plus 1. I'm going to add that to 2 times 2 cubed minus 2 squared plus 1. I'm going to add that to, and I'm going to keep doing that until I end up with 2 times 100 cubed minus 100 squared plus 1. I'm going to add 100 things that look like this. Now, how do we actually do that? Well, you wouldn't want to actually do this by hand, and so the formulas I gave you earlier can make it actually a lot easier to add up those 100 things. I mean, it will still be kind of a little bit annoying, but not nearly as annoying as doing it directly. So one thing we can notice is by this property over here, the series can distribute across these sums of terms. By the property I just erased, this 2 here is a constant. I can factor it outside. And now you notice that I have the sum of I cubed, the sum of I squared, and the sum of 1, which we have formulas for that. And so ultimately this would look like, well, it's going to be 2 times the sum of I cubed. The formula for that is n times n plus 1 all over 2. Of course here we're assuming that n equals 100. I'll plug that in afterwards. I just wanted you to see me plug in the formulas. It would be minus n times n plus 1 times 2n plus 1 all over 6. And this, of course, will be, well, 1 times n. And if I plug in n equals 100, this will all add up to 2 times 100 times 101 over 2 squared minus 100 times 101 times 201 all over 6 plus 100. Now it'll take you a little bit of algebra to kind of simplify that into one thing, but it'll be a lot easier than actually adding up 100 things. So you see that once we get the series notation and we develop some formulas to add up certain kinds of objects, we can add up combinations of objects that get progressively more and more complicated, and we can do it with a lot less brute force than we would have had to do it, right? So I wouldn't want to be adding stuff 100 times. I can just apply these formulas, and then it's just me reducing. So it's one way in which series are really beneficial. Not only is the notation concise, we can, instead of listing off 100 things, I can write down 3 things, and it will be almost like listing off 100 things. And then I can add them pretty easily using these formulas. Now again, you'll see many different kind of sums in Calculus 2, but here's a cool kind of sum. Which you will see again, but I'd like to introduce it in Calc 1. It's called a telescoping series. And basically what a telescoping series is, it's a series in which, when you start adding the terms, you realize that a lot of them, in fact most of them, cancel themselves out, so you don't actually have to add as many terms as you thought you had to add. So sometimes you have a thing that you don't really have a nice formula for, but it turns out you didn't really even need that formula in the first place. So these are a series where most terms cancel themselves out. So, example, let's say you wanted to find the summation of something that looks like this. Let's say it goes from 1 up to n, right? Of that expression. So the first thing I want you to notice is that there was a reason I didn't tell you about how to take the sum of a division, because we don't really have a nice way to do that. We don't have a nice way to, series don't behave well under multiplication and division, by the way. So let's just make a note of that. Probably should call it a warning, just in case you ever have the urge to do it, you know that you can't. Series do not distribute across multiplication and division, and hence division. Why? Well, if you're finding the series of something that is like this, ai times bi, that means you're finding a sum of terms that look like that. Whereas if you were to actually think that you can distribute the series across the sum, what you have to notice happens in this case is that this guy means I'm adding up a bunch of a's, and this guy means I'm adding up a bunch of b's, and then the distributive law would take effect. Once you start multiplying out, you'll get way more terms than you have here, right? Because not only would you get a1 times b1, you'd get a1 times b2, a1 times b3, you'll get a bunch of terms that's not present here. So these two are not the same, they're not equal. You can't actually distribute a sum across multiplication. You can only do it across division. Okay. So that being said, you can only do it across addition. Okay. So if it doesn't work for multiplication, it can't work for division either. And so we kind of can't like distribute our series the way that we did before. However, you'll realize that in this case, we actually don't need to be able to do that. If you start actually adding these terms up, what would the first term look like? Let's see if we remember how to read these things. What's the first number here? Yeah?
It'd be 1 minus 1/2.
1 minus a half. So that happens when I equals 1. When I equals 2, what would you get?
1/2 minus a third.
1/2 minus a third. Next term would look like a third minus a fourth. Next term would look like a fourth minus a fifth. Dot, dot, dot. If I keep going, let's say dot, 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 plus, let's say here, my I is equal to, say, n minus 2. So here I would have 1 over n minus 2 minus 1 over n minus 1 plus 1 over n minus 1 minus 1 over n plus 1 over n minus 1 over n plus 1. So this will be the third to last term, the second to last term, and the last term of this sum. Now what you'll immediately start to notice is that we have a bunch of these guys canceling out. I have a minus a half and a plus a half, minus a third and a plus a third, minus a fourth and a plus a fourth, minus a fifth. The next term is going to give me the plus 1/5, so this is going to cancel out with the very first term over there. Here, this cancels that, this will cancel that. This guy will cancel with the last term in the previous term, right? That would have had minus 1 over n minus 2. So pretty much what you see here is this guy starts out being a lot of terms, however, most of them actually kill each other. So it ends up being that to add up these things, we only have to actually add, well, pretty much 2 things, this and that. It turns out that this is equal to 1. I would get that expression. Right? And here my n could be any positive integer. Right? So I could do this for up to 1,000 terms, and then I can add a difference of fractions 1,000 times. And it turns out that the result of that will be 1 minus 1 over 1,001. And that's nice. That's called a telescoping series, or a telescoping sum. Not sure why they use the word telescoping here, but that's what it's called. It's another kind of series that we'd like to know. What other examples? Now I want to get to the sophisticated stuff, adding up an infinite number of things. What does that even mean? In order to talk about that, I have to define something else for you. I will need to define what we call a partial sum. So let S equals this be a series. So I go from 1 to n. We define the nth partial sum of S by this expression called Sn, and basically it is the sum of the first n terms. Let's make this an uppercase n. It's basically the sum of the first n terms of the series. So it's a1 plus a2 plus a3 plus all the way up to a little n. This is called a partial sum because in general you're assuming that your n is not the entire thing, it's just a part of the thing. So if I have a series that goes from 1 up to uppercase n of ai, so I know this is just a1 plus a2 plus a3 plus da, 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 all the way up to a big N. Okay? I can talk about the partial sums of this series. So I can talk about the partial sum of the first term. Well, that is literally just a1. I can talk about the second partial sum. Well, that just means a1 plus a2. I can talk about the third partial sum. That's a1 plus a2 plus a3. And I can talk about the fourth partial sum, a1 plus all the way up to a4, and so on. And I can go all the way down to the s uppercase n, and that will literally be the entire series in this case. Right? So these guys are called the partial sums. Now what you would notice about the partial sums is the following. The partial sums will form a sequence that we can talk about, and this sequence is called the sequence of partial sums. Because math people are great at naming things. That's literally what it's called. You can find the sequence of partial sums. And it means that you're just thinking of these guys here as a list of numbers. Right? You can think of them as a list. And ultimately what you would notice is that this list, the terms in this list, so this is just a list of things, the terms in this list, you will notice that Sn will approach what the actual sum is as n approaches the endpoint, right? So what you're noticing is these numbers are successively getting closer and closer and closer to the entire sum, right? They're just doing it one step at a time, right? And so they're getting close overall. They might jump up and down here and there, but overall, they would end up where the entire sum ends up. Okay? So the sequence of partial sums, assuming S is a thing and it can actually add up to a number, if you look at these numbers, they will eventually add up to what number you should get. So again, if we looked at that Gauss's story example, where you had to add up the first 1,000 numbers, the partial sums would be, well, they would start at 1, then 1 plus 2, then 1 plus 2 plus 3, then 1 plus 2 plus 3 plus 4. Now these are giving you different numbers. That will give you 1 and 3 and 6 and 10 and so on. But what you're noticing is these numbers are increasing towards 1,000. By the time you get to the end of that list, you will hit 1,000. Okay? So that's the idea of a partial sum. And this is called the nth partial sum. And what you can notice about the partial sums is the sequence of partial sums will approach the actual answer. And so now we can talk about something that at first might seem nonsensical, but it will actually make sense. And we can know that it makes sense because of the results that we can obtain. So we did that. I spoke about that example last time about us shooting an arrow at a target, and we kind of conceptually thought about this as the arrow covering half of its distance ever so often. And so you can kind of think of that situation as you're adding up a bunch of half distances, and on one side it seems like you'll never actually hit the target, but then in reality you of course realize we do actually hit the target. It is possible to dissect a finite number into an infinite number of things. And that is a very important idea. Now, how do you actually put the math behind this idea is by taking this idea to its extreme conclusion. Right? So the idea is if we're looking at the partial sums, they will get closer and closer to the actual answer. Well, what if you wanted to have an infinite number of partial sums? Well, that would simply require you having your big N be infinity. And so with the above idea, we can define this sort of object. A sum which adds an infinite number of terms. Now I might be able to talk about what those terms individually would look like. But what does it mean to add up an infinite number of things? Well, it's going to be, well, it doesn't really make sense to add an infinite number of things in the beginning. So what you start to do is you add up a finite number of things. You start adding up the partial sums. You only add n terms at a time. So sure, ultimately I want to be able to add an infinite number of things, but let me start by adding one thing, then adding two things, then adding three things, then adding four things, then adding five things. And you keep going, and basically what you do is you let n go to infinity. So we can we can define the sum of an infinite series to be the limit of a sequence of partial sums. Where this is literally going to be Sn, as I described earlier. So an infinite series is just the limit of its sequence of partial sums. And again, you can actually do this, you can do this example. A nice one to do would be to say, okay, imagine you're 1 feet away. Start cutting that, add those half units. Add up a half to a quarter, to an eighth, to a 16th, and apply this formula, and you'll realize that you will get the answer 1. So you can actually do. So we know that it actually works for us to think about this idea. Right? So we actually use a limit to help us get there. And that's how we can add up an infinite number of things. Let's actually put this into practice. We are going to do this in context pretty soon. I think pretty much by next class, end of next class, or the beginning of the following class. We're going to be doing this like within context. So let's just make sure we have the mechanics down. Suppose I wanted you to compute this. So you have a series, and for some reason it looks like this. This particular series has a lot of meaning, and which I'll talk about. Pretty much one of our first examples where I'm actually going to tie everything together to finding the areas under curves. That's what our first example is going to end up looking like. So once we get to this point, how do we actually deal with it? Well, there are a couple things. One, I can rewrite a little bit. This is just 1 over n times I squared over n squared. Secondly, you will notice, remember I is the variable. You can tell who the variable is by looking at the index of the series. So this guy is the variable. Turns out that the n's themselves, I can consider them as constants. And so what I can do is I can factor them out according to the earlier property I mentioned. So I can factor out a 1 over n cubed, and then I'd be left over with the summation of I goes from 1 to n of I squared. And I want to take the limit of that. And so now, what I can do is I actually know what this is. I have a formula for that. Right? So all those formulas that I mentioned earlier, you have to have them memorized. So whenever they pop up suddenly, you can now replace that guy with the formula. So this ends up being the limit as n approaches infinity of 1 over n cubed times, applying this formula, I will get n times n plus 1 times 2n plus 1 all over 6. By now we should be expert at limits. You should be able to tell me that limit. What's that limit? Yeah? 2? No.
1/3.
It's 1/3. How'd you get that?
The degree is same in the denominator.
Right, infinite limit, ratio of polynomials. The highest part on the top would be n cubed. So the top is 2n cubed plus a bunch of stuff that we don't care about because we're going to infinity. The denominator is 6n cubed, so it goes to the ratio of coefficients. So it goes to 2 over 6, which is 1/3. So essentially, I want you to realize that what we were actually doing is like, it's equivalent to saying this. So basically, we just did an example. We added up an infinite number of things just now in a finite amount of time, and it turns out that these infinite number of things added up to 1/3. Probably kind of weird to think about, but that's the answer. So in some sense, it's like you know that the sum will never pass 1/3, but then at the same time, if you pick any number less than 1/3, the sum of the series will eventually pass that number. So you can apply something like the squeeze theorem and basically say that, oh, it has to be 1/3.
I have a question.
Yes.
How is there 2n plus 1 instead of?
Well, that's the formula.
Plus
The sum of I squared is that n times n plus 1 over n times n plus 1. Make sure you wrote it down probably the first time.
2? N plus 2.
Yeah, no, it's 2n plus 1. You guys probably feel like I did a lot of voodoo there, but unfortunately, not much more I can say about that at this point. You'll talk again a lot more about series in Calc 2, and honestly, even then you probably won't be comfortable with the idea of a series and adding up an infinite number of things and getting a finite answer. You probably have to take a class like Advanced Calculus or Real Analysis before you start really getting comfortable with something like this. And it doesn't like keep you up at night. What? But I'm adding forever. How come I can stop? Like, what do you mean? Like, no, it stops at 1/3. It's actually 1/3 is the answer. So now I want to. This is what we're going to go into more tomorrow. But I just want to give you sort of an idea of where we're going to be using this. So let's do an example for tomorrow. Okay, so here's the idea. Say I had the function y equals x squared. So that's my f of x equals x squared. Okay. And I wanted to find the area under this curve between 0 and 1. So I care about this area here. Now this is one of the first steps towards solving the area problem. You'd realize that, okay, so here's this blob that I want to find the area of. That's already too complicated. Math people like to start with a simple case. So what we imagine is that, just throw this in the xy plane, and for the first part, let's not worry about the bottom. Let's find a strategy for how to find the area of the top. And so they start doing what they always do. They're going to dissect it. Now you don't want to dissect it in two. Now before we did that, and we did a patchwork of things, but that's kind of complicated to do math-wise because that is what would turn out in a multiplication of series. Because you'd have one series has to be counting the vertical while the other is counting the horizontal. So we don't want to do that. So our idea then becomes, you know what, let's just slice things in one direction. Let's slice it vertically. So let's say I cut this area into 4 slices, right? And let me name these things. So call this right endpoint, you can call that x0, This x value I'm going to call it x1, that x value I'm going to call it x2, that x value I'm going to call it x3, this one I'm going to call it x4. So I split up the x-axis under that graph into 4 sections. And again, just to keep things simple, I'm going to imagine that I cut this into 4 sections evenly. So I'm going to call the distance for all of them is going to be what I call delta x. I'm going to cut up this interval into 4 equal sections. Clearly here you'd of course know that this is 0.25, that's 1, that's 0.75, that's 0.5, that's 0.75, that's 1. Okay. So now, obviously the area of this entire thing is just the area of all these 4 pieces added together. But again, I run into the same problem. I have a very weird shape in the top. I don't know what it means to find the area under this shape. So what instead I would do is where each of these lines hits the curve, I'm going to stop it, I'm going to cut straight across and create a rectangle. I'm going to do the same thing here, cut straight across, create a rectangle. Come here, cut straight across, and make a rectangle. And so here's my idea. I will now look at the areas of these rectangles. And basically the idea is I want to approximate the area under the curve by the sum of the areas of these rectangles. So that's my idea. Now obviously you can see from this picture I'm not going to get the exact answer. There's a lot of space missing here. Okay? So of course when I add up the areas of these rectangles, I'm not going to get the right answer. In fact, I can clearly see in this situation that I will get an underestimate for the area. I'm going to get less than is the actual answer because I'm missing a lot of pieces. It's also worth mentioning that had I put in more rectangles, maybe doubled the amount of rectangles, I would miss even less. And then you can be like, oh, well, I can even do more rectangles and miss even less, right? So we have this idea in the back of our minds that we would be able to do this, but let's actually just figure it out for 4 rectangles. Okay. How do we go about finding the area of these rectangles? Well, we know the area of a rectangle. It's going to be length times height, or width times height, or whatever you want to call it. How would we figure out the height of these rectangles? Well, the height is determined by a function. I went up, and when I hit that function, I cut across. So it turns out that I would know what the height of this rectangle is by just plugging that x value into the function. Similarly, I would know this. I would know this. This is x2. It turns out that the first rectangle is actually a rectangle of 0 height. Technically, I would have f of x0 is of course 0. So I'm thinking there are 4 intervals here, so there are 4 rectangles that I'm imagining. The first one just is too small to notice. So in other words, I would say here that my area, therefore, is going to be approximately equal to the sum of the areas of these rectangles. And what would the sum look like? Well, it would be length times width, length times width, length times width. So I would have f of x0 times delta x plus f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x. So basically, to find an approximation for this area, I am going to have to calculate something that looks like this. Now, one thing that's very nice about the thing that looks like this is it follows a pretty identifiable pattern here. It's always f of something times delta x, and the something has subscripts that are counting up by 1 unit each time. This sort of gives me an idea, hey, I can actually just talk about this as a series. I can think of it as f of xi times a delta x, where I would let my I count the subscripts. So here I'd say I goes from 0 to 3. And I can talk about the area of these rectangles as a summation that looks like this. Now this, by the way, has a very special name. This is called, of course, I'm adding up a finite number of rectangles, hint, hint, and this is therefore called a finite Riemann sum. Now Riemann is the name of the mathematician that came up with this method. There are actually many methods for finding areas on the curves, but Riemann, I forgot the actual date, late 1800s, early 1900s, came up with this process for integration, and he came up with it in his thesis for his PhD, of all places. So in his thesis for his PhD, he wanted to talk about some things which required him to reimagine certain things that we knew about calculus at the time, and this was how he reimagined the integral. So the area under the curve, as we're going to be doing, is due to Riemann. It will be basically us computing Riemann sums. And they're pretty much sums that look like this. They're pretty much sums that describe you adding up areas of rectangles under a curve. And next class, we're going to actually make this a lot more precise. This is just an example to get you used to the idea. And then, hopefully by the end of next class, which I think we'll be able to use this process to find the exact area under the curve. No missing gaps, no approximation, we'll know what the area is. But until then, we'll stop there. We covered everything I want to talk about, summation, series now. Now we're just going to apply them to actually solving the area problem. We're going to solve the area problem the way Riemann did in the early 20th century. So we'll see you guys tomorrow.